Alright, welcome back guys. In this semi-short video, I'll be covering the concept of differentiability in functions. As many syllables as that word has, all it means for a function to be differentiable at a point is that its derivative is continuous at that point. And remember, for us to take a derivative in the first place, the function itself has to be continuous at that point. So pretty much what I'm saying is differentiability, or for a function to be differentiable, it already implies that the function is continuous. Okay? It's kind of like saying, my name is Anderson and I live in Florida. It goes without saying then that I live inside of the United States, because living within Florida already implies that I live in the United States. So again, for a function to be differentiable, it implies that the function itself is already continuous along with the derivative needing to be continuous. So let's go ahead and take a look at a problem that you might see in the classroom or in an exam regarding differentiability. So for example, let's say we had the function f of x, and it's defined as a piecewise function. And for the most part, yeah, you will see piecewise functions because regular functions are already continuous on their own, and they already are differentiable because when you take the derivatives, it's a nice smooth curve. So for the most part, you will be seeing piecewise functions. So let's say that we had, this first piece is 3x squared, and this is only defined when x is less than 1. Let's say we also have another piece, say, mx plus b, and this is only defined when x is greater than or equal to 1. What we need to do here is find out what values of m and b will make this function differentiable. So you need to be very careful with how you tackle these types of problems, because you could think that, oh yeah, as long as they are continuous at x equals 1, that's all I need. And if you were to do that, to make this continuous, all we need to do is set these two functions equal to each other and set x equal to 1, because they would need to have the same y value at that point for it to be continuous. And you're not wrong for beginning like that, but we need to also acknowledge that we have to have continuity on the derivative as well. So just keep that in mind. If we were only tackling continuity on f of x, we would see that we would set these two functions equal to each other, just like so, equals mx plus b. But the thing is, look, this statement is only true when x is equal to 1. It has to be true when x is equal to 1. On their own, so if we were looking for the entire continuity here, on their own, 3x squared is continuous on its own. Mx plus b is the equation of a line. And as long as m and b are real numbers, it could be 0 too, because that's a real number. This would be continuous on its own because it could be a horizontal line or a line. And so that's fine. So if we were to do this when x equals 1, we would substitute 1 for x, leaving us with 3 times 1 squared, or 3, equals m times 1 plus b, or just m plus b. And boom. And if you're left here, with this relationship, because remember, if we have two variables in one equation, this is called a relationship. And, we could take guesses at what m and b are. We could guess that m is 0, b is 3, because that would totally make sense. We could say that m is 2 and b is 1. That would also make sense. And I hope you noticed that we can have an infinite set of values for m and b that will make this relationship true. And yeah, that's absolutely right, because we can actually pick, an infinite set. But that will only give us continuity in f of x. That will not make this function differentiable, because remember, the differentiability means its function's derivative is continuous throughout. So we need to go ahead and take it a step further by setting their derivatives equal to each other when x is equal to 1. So let's go ahead and do that here on the side. I'm going to go ahead and compute the derivative of both of these functions and set x equal to 1 afterwards. So the derivative with respect to x of 3x squared needs to be equal to the derivative with respect to x of mx plus b when x is equal to 1. So when x equals 1. That will make this function differentiable. So in tackling this, we'll set x equal to 1 afterwards, because if we set it equal to 1 first and we take the derivative, we'll get 0 on both sides. So let's go ahead. The derivative with respect to x of 3x squared, well, that would be 3 times something squared. So the derivative of 3 times something squared would be, well, 3 times the derivative of this. So that would be 2 times that something raised to the first power times the derivative of that something, applying that chain rule with respect to x. So the derivative of that something with respect to x. And yeah, we should know by now this will reduce to 1, but I'm just overemphasizing the chain rule. So up next, we have the derivative with respect to x of a sum. And again, that would just be the derivative of the first plus the derivative of the second. So the derivative of mx. All right, if this confuses you, remember, m is a constant. M is a constant, so it's kind of like treating it as 5x. The derivative of 5x is just 5. If it were 12, the derivative of 12x would be 12. Because remember, this is a constant. The derivative of a constant times a function is the constant times the derivative of the function. So this would just be m times the derivative of x, or just m times 1, which would be just m. Then we have the derivative of b. Well, that's a constant as well. If it were 5, that would reduce to 0. If it were 12, reduce to 0. If it were infinity, the derivative of a constant is 0. So that would be 0 plus 0. And I'm going to save some space, or save a line, by just erasing it now. Over here, 3 times 2 times x to the first, that's 6x, times dx, that's just going to be 1. So this means that 6x needs to equal m when x is equal to 1. So now, here we had this relationship. Here we can actually solve for m, because now we can plug in x equals 1 and see what happens. So if we plug in 1 for 6, we'll get 6 equals m. And there we go. We now have our value for m. We now have the slope of this line that we'll need to have. And this should make sense, because if we look at the derivative of 3x squared at 1, we're looking at the rate of change of 3x squared when x is equal to 1. And like we saw, the derivative of 3x squared is 6x, and at 1, the slope needs to be 6. So its rate of change is 6. So it only makes sense that this line has the slope, the same slope that 3x squared does at 1. So now all we got to do is substitute m over here and solve for b. So in doing so, we'll have 3 equals 6 plus b. And then upon subtracting 3 from both sides, we'll receive, well, not subtracting 3, sorry about that. Upon subtracting 6 from both sides, to isolate b more easily, we'll receive negative 3 equals b. And that's it. We're done. We are done. This means that for this function to be differentiable at x equals 1 and throughout, we'll need m to equal 6 and b to equal negative 3. So let me go ahead and just erase this over here. That way we have room for this graph that's coming in right overneath. Boom. So let's take a look at the graph. We see that, yeah, this function is a parabola all the way up until x equals 1. And then at x equals 1, let's go ahead and zoom in there. Check that out. That's really cool, because the slope, that curve is flowing very, 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 very nicely. It's almost like it picked up right where it left off. It doesn't look like a corner or a cusp. It kind of looks like it just keeps going where it took off, but just in the form of a line. And that's what differentiability is. It's a nice continuous slope. A nice continuous slope on the curve. So essentially, differentiability is an extension of that conversation of continuity. It's extended to the derivative. Now, let's go ahead and take a step back. So let's take that graph away. Now, remember earlier when we just had 3 equals m plus b, before we decided to look at the derivative. Again, 3 equals m plus b, we can guess at whatever values we want for m and b. So let's say we chose 0 and 3. So let's take a look at the graph. If we chose 0 for m and 3 for b, notice it's a parabola all the way up until 1, and then, in this case, it's a horizontal line. Horizontal line at 3. You see that corner? That corner right there means that although this function is continuous, it is not differentiable at x equals 1, because the slope changes so dramatically. It's like a jump discontinuity on the slope. And so let's check out the derivatives. So if m was 0 and b was 3, yeah, look at the graph of their derivatives. There is a jump discontinuity at x equals 1. And so because the function's derivative is not continuous at x equals 1, this function is not differentiable at x equals 1. So I hope that makes a little more sense in terms of what differentiability means. You'll likely have a lot of problems like this where you'll be given a piecewise function and you'll either be asked to find if the function is differentiable at a point with what they give you, or they could do what I did and they could give you, two variables and say, hey, find out the values of these variables that will make this function differentiable at a certain point. And they could give you one variable or more than one variable, depending on how many pieces you have. But for the most part, there's a general guideline that you can follow for all of this. So if you're asked to find if a function is differentiable at a certain point or interval, and there aren't any arbitrary values, like m or b or, k, a, b, c, no arbitrary values. The function is, there's only one variable, and that should be x, or the independent variable. The first thing you got to ask yourself is this function continuous on the interval or point in question? And, if it's a piecewise function, pretty much all you got to do is just set the pieces equal to each other and set x equal to the point at which they meet. And you can find out if it's continuous first. And if it's not continuous at that point or interval, then, it can't be differentiable. Because for a function to be differentiable, it first has to be continuous. And so automatically at that point, you can just say no. But let's suppose that it is continuous at that point. Now, if it is, to find if it's differentiable, then you want to go ahead and take the derivatives of both of those pieces and see if the function's derivative is continuous at the point by setting those pieces again equal to each other. But this time, it's their derivatives that are being set equal to each other. Now, if you have arbitrary values, for a point or points, it's the same process, but you're going to set the pieces equal to each other, that meet equal to each other, and then input the appropriate value for x. So for example, if one function leaves off at 2 and the other starts at 2, you'll set the pieces equal to each other and set x equal to 2. And when you do this, when you simplify, you'll most likely have a relationship. If it's one variable, then you'll probably have a solid value for that variable. But if there are two variables involved, you're most likely going to have a relationship. And that's completely fine. Just leave it the way it is. Because afterwards, you're going to take the derivatives of those pieces, those same pieces, and set them equal to each other again, and do the same thing. Set x equal to that appropriate value at which they meet, and then see what we have, what relationship we have. Because more likely than not, you might have something reduced to maybe, just one variable because one of the other variables was by itself, or one of those other arbitrary values, one of those arbitrary values was a constant value, and it could have gotten reduced to 0. And so that's really good for us in terms of setting that derivative equal to each other and getting the value of one of those arbitrary numbers. And that's pretty much it. So, to recap, again, differentiability means continuity as well as continuity within its derivative. So that's all it means. It's just an extension of that conversation of continuity. Differentiability implies continuity. So as long as we can understand that, we're in great hands moving forward. Just keep practicing problems like that, because I promise you, you will see a problem like that in an exam. That's definitely one of those huge concepts to cover. So go ahead and watch the next video on this. Keep practicing and mastering, and we'll catch you next time. Have fun.